Good afternoon, everyone. My name is Myoungsung from the University of Seoul, and it's an honor to present our paper here. And today I am presenting our work on HybridMesh, hardware-software hybrid approach for accelerating service mesh ingress. This is joint work with Dankook University, ETRI, Chonnam National University, and KAIST. Let me start with some background. Service mesh is the de facto standard for implementing microservices in cloud environments. It provides various inter-service communication logic, such as load balancing, security, and service discovery in a separate array of proxies. So applications don't need to implement this infrastructure layer functionality in themselves. A service mesh consists of two kinds of proxies, sidecars and the ingress gateway. Sidecars are deployed alongside with each application and handle traffic between microservices. On the other hand, the ingress gateway acts as a centralized entry point for incoming traffic and distribute packets to each service. So now let's zoom into the ingress gateway. This is where our story begins. Our external traffic enters the service mesh through this proxy, and it has two main tasks. The first one is routing. It inspects incoming packet headers and payload and parse layer segment fields such as host name, URI path, and allowable user-defined ones, and matches them against a number of routing policies to distribute the packets to correct destination. Second, traffic management. The ingress gateway also load balances packets across multiple paths belong to the same service. For example, it caps concurrent requests to a given path to a predefined circuit limit. If the destination path is temporarily unavailable, the ingress gateway buffers the request and retries sending the packet to predefined retry limit. But despite this central role, the current ingress gateway suffers from serious performance problems. There are two main reasons. The first one is CPU-intensive traffic analysis. Microservices usually communicate over layer 7 protocols such as HTTP-based REST API. The gray box on the left side shows a typical ingress gateway configuration. It matches a host URI prefix and sets a timeout and retry count. It looks benign, but under the hood, for every single packet, the gateway has to parse various layer 7 fields such as host and URI prefix and run regular expression matching against thousands of such rules to determine the correct destination, running many CPU cycles. We profile the East-tier ingress gateway's operation, and as you can see in the table, traffic analysis and matching alone takes about 39% of total CPU cycles. So the second problem is the long and complex packet forwarding path. In a typical cloud environment, the gateway and each path run in separate network namespaces. So when a packet arrives, it goes up to the ingress gateway and come back down to the root namespace for virtual switch processing, and then goes into up again the destination path. This causes two problems. First, repeated network namespace crossing between the gateway and the destination path. Second, repeated TCP/IP stack processing. TCP/IP is handled twice for the same packet during this path. And this happens for every single packet, so degrading the overall performance. To measure the impact of these two limitations, we conducted a simple experiment on Kubernetes-based environment, even with just one policy that route packets with predefined URI pattern across a set of Nginx path. Going through the gateway dropped throughput 2 times and doubled the latency. 4 times and doubled the latency. And as you can see in the right graph, so as number of policies grows, the problem gets much worse. With 256 policies, throughput drops by 6.5 times and the latency increased by 18 times. This is the problem we want to solve here. Now, let's think about how to solve this problem. there are two existing approaches. The first one is software level optimization, such as implementing eBPF or shared memory-based data channel between the gateway and endpoint path. That works to a point, but you are still running many CPU cycles on the Ingress gateway. In cloud environment, those cores should go to the actual tenant workload rather than this infrastructure layer functionality. So software alone is not enough. The second one is full hardware offloading. Prior work attempts to offload some traffic dispatching and routing mechanisms to dedicated hardware devices, such as people switches and FPGA-based SmartNICs. But due to the limited flexibility of these devices, they cannot fully support rich traffic management features required for service mesh ingress processing. Modern SoC-based SmartNIC offer general-purpose only cores such as ARM or RISC-V cores for complex processing, but offloading the entire Ingress gateway there is also a bad idea. This is because the gateway also contains some control-intensive tasks such as TCP/IP processing, request buffering, and error handling. These tasks are unsuitable for hardware accelerations and can make the WinP-only core overloaded. So neither extreme works on its own. We need something in the middle, and that is exactly what HybridMesh is. HybridMesh takes a hybrid approach using both the SmartNIC and CPU cores together. We then split the gateway's task by their nature and run each one on the right processor that can handle it best. This hybrid design gives us the balanced performance and flexibility. The core idea of HybridMesh is simple, disaggregation. We broke down the Ingress gateway into 4 similar tasks and analyze each one and assign it to the process that handles it best. First, the compute-intensive tasks, the yellow one. These tasks are suitable for hardware acceleration, so they are uploaded into the NIC stack implemented on the SmartNIC. Second, the control-intensive tasks, the green one, including traffic management and traffic relaying. These tasks are unsuitable for SmartNIC and is only core, so they stay on the CPU side and processed by our lightweight CPU side proxy called the node stack. And finally, we use eBPF to bridge these two stacks and each endpoint path so that packets flow between them efficiently. Let's go a level deeper into the NIC stack. When the NIC stack receives a new packet, it first performs network level matching and tags each packet with its access point. An access point is an IP and port group assigned to each service. Based on the access point matching results, the RSS engine in the middle assigns packets to the right only core while keeping the same connection on the same core. The traffic dispatchers running on these only cores then receive these packets and parse their layer 7 field, run regular expression matching using hardware accelerators, and find the destination service and destination path. The matching result is then inserted into the packets layer 2 header as 6 bytes of metadata, so the next stage know exactly how to handle this packet and where to send it. Now let's move to the node stack, which run on the CPU side. It handles the complex control-intensive tasks, which are unsuitable for SmartNIC. With a HybridMesh, the node stack has to perform heavy layer 7 parsing and a number of regular expression matching for every packet to determine the right policy and the destination. With HybridMesh, the NIC stack has already done that work using hardware accelerators and inserted the answer into packets metadata. So the node stack only needs a simple exec or prefix-based matching on this metadata. So after that, it applies required traffic management features such as circuit breaking, fault injection, and traffic mirroring, and then forward the packet to the determined destination path. Now, let's talk about the hybrid mesh tunnel, the HMT. It runs at the kernel space and streamlines the long packet forwarding path between the gateway and the endpoint path and destination path. In a conventional gateway, packets go through many layers, including the virtual switch and causing repeated namespace crossing and network stack processing. With HMT, we cut this path using two eBPF tricks. First, interface merging. We make the NIC and NIC stack and the node stack directly exchange packets via a single virtual interface. So packets now skip the virtual switching. And second, socket redirection. When the node stack send the data to the destination path, the HMT intercepts the data and copies it from the source socket to the destination socket without involving the kernel network stack processing. So the packet forwarding paths become much shorter and much faster. Now implementation details. We implemented the NIC stack on an NVIDIA Bluefield 2 DPU, and it runs as an DPDK applications on the ARM cores using Docker API to upload the regular expression and crypto operation to dedicated hardware. The node stack is built on HA proxy with custom HTTP filter for metadata-based routing. And the HMT is implemented with 3 different eBPF programs, including XDP, TC, and socket messaging. Now let's see how hybrid mesh performs. We compare hybrid mesh in Navy against 2 software Ingress gateways, ETRI Ingress and NGINX Ingress. Look at the left chart. As we increase the number of CPU cores allocated to each gateway, hybrid mesh quickly reaches near the direct baseline, which bypasses the Ingress gateway processing at all. As shown by the red box, hybrid mesh with just 4 cores outperform ETRI Ingress running on 20 CPU cores and by up to 4.4 times. In addition, hybrid mesh remain stable even when handling 1024 policies due to its hardware accelerations. However, ETRI Ingress dropped sharply because its CPU cost grows every added policy. Performance is great, but in cloud, cost and power matter just as much. We compare 3 configurations shown in the table. CPU only is ETRI Ingress with 20 cores, and SmartNIC only is the fully offloaded version of hybrid mesh. It runs both the NIC stack and node stack by using the SmartNIC's only core. And SmartNIC hybrid is our original hybrid mesh with 4 CPU cores. There are 2 takeaways. First, SmartNIC only saves powers, but its performance is limited and even lower than CPU-only designs. This is because the only cores get overloaded with control-intensive tasks, preventing the SmartNIC from performing other compute-intensive tasks. Second, our hybrid design wins on both sides. As you can see in the red box, it achieves 2.3 times better cost effectiveness and about 3 times better power efficiency than CPU-only designs. So let's wrap up. Software Ingress Gateway has become the main performance bottleneck in modern service mesh environments due to its CPU-intensive traffic analysis and long packet forwarding paths. And they burn many CPU cycles that should go to actual tenant workload. So our solution is hybrid mesh, hardware-software hybrid Ingress Gateway. The idea is simple. We split gateways tasks and offload compute-intensive tasks to the SmartNIC while keeping the control-intensive tasks on the CPU side. This hybrid design not only improves the performance, but also provide rich traffic management features as software gateways, and it improves the cost effectiveness and power efficiency. This is end of my slide, and I thank you for taking your time, and I'm happy to take any questions.